Hello everyone, this is Sai Shri. In this video, we are going to explore the advanced pruning strategies that extend the concepts of minimax and alpha beta pruning to handle the challenges of multiplayer decision making. In AI, minimax and alpha beta helps to make smart decisions in two-player games like chess and Go. What about multiplayer games? With multiplayers, the search complexity increases. The maxent algorithm extends the minimax to multiplayer setup, but it weakens the power of alpha beta pruning. This study explores shallow pruning, deep pruning, immediate pruning, alpha beta branch and bound, and hybrid pruning techniques. We also explore paranoid approach, which on high level is a reduction of multiplayer settings to a two-player format to make the search more efficient. Here are the examples of multiplayer games. First is a Hearts. This is a four-player game with 52 cards. The objective is simple. Players avoid collecting the points. Each heart is of worth 1 point, while Queen of Spades is of 13 points. Lowest score wins the game, but there is a catch. Shooting the moon. Shooting the moon is a scenario where the player collects all the 26 points, that is 13 hearts and queen of spades. He can make his score 0 and add 26 points to all other players. In AI, hearts is a minimization game. The limitations are limited pruning and making efficient decision harder. The second game is a Sergeant Major game. This is a three-player trick taking game. This is a three-player trick taking game. Here, goal is to win as many tricks as possible. Each player must follow the leading suit. The highest card player wins the trick. To win the game, player needs to win more tricks. Unlike hearts, this is a maximization game. While shallow pruning can be applied to make search more efficient. What is this duality of maximization and minimization? Both maximization and minimization are symmetric to each other, so we can convert maximization setting to minimization or vice versa. For example, here hearts is a minimization problem, where players with least number of points wins the game. To convert this into a maximization, we subtract the scores of all players from a constant so that the players try to maximize the difference. Minimax algorithm for two-player games. Before exploring the multiplayer game, let's brush up the concepts of minimax in two-player games. In Minimax, one player tries to maximize the score while others tries to minimize it. The AI looks ahead all the possible moves, assigning each outcome a utility value. Since it's zero-sum game, one player gain is another player's loss. By looking ahead, choosing the move carefully, Minimax ensures the best possible outcome, no matter what the opponent does. This is simple but a powerful algorithm, the foundation of AI in strategy games. Okay, AI decision making in two-player games uses minimax, but what happens when there are more than two players? Here comes the Maxent algorithm. Maxent extends the minimax to a multiplayer setting. Instead of single value, each node stores a n tuple, uh, n tuple where each one is a score for each player. Unlike in minimax, here each tries to maximize their own score. Every move affects all the players. The AI evaluates the future outcomes, chooses the moves that gives the highest personal advantage while considering the opponent's strategy. Let's break down the example shown here. At top we have the root node where player 1 is making the move. Each number represents a player's score. Player 1 has three choices A, B, and C. The decision tree expands as the game progresses. Now it's player two's turn. Each child node shows how the score changes based on the player's choice. For example, player 1 chooses B. The state is 0, 10, 0, meaning player 2 has 10 points. A very strong move for them. Making next, player 3 makes a move aiming to maximize their own score based on the player two's choice. The bottom of the tree shows the final scores after all the three players have made their decisions. One key AI technique here is the immediate pruning. Since player 2 has already got the 10 points at B, they don't need to explore further. This helps AI eliminate unnecessary calculations, making decision making faster and more efficient. Here are the limitations of alpha beta pruning. Before As the number of players increases, search tree also grows exponentially, which makes the search exponentially expensive. In two-player games, alpha beta helps eliminate unnecessary branches, but in multiplayer games, alpha beta becomes less efficient as there is no strict best first opponent dynamics. Maxon assumes all the players act independently that maximize their own score, but in real games, players sometimes form alliances. This makes Maxon unrealistic in the games with temporary cooperation like Risk or Poker. Maxon works best in the perfect information game where all moves are visible, but in games like Poker, AI doesn't know all, all the cards. Since Maxon assumes full information, it struggles in hidden information games, making it unreliable. By improving pruning, uh, predicting alliances, and handling hidden information, we can make AI more efficient in multiplayer games. So far, we have discussed the fundamentals of decision making in multiplayer games and the limitations of traditional algorithms like Maxon. Now let's explore how pruning techniques help optimize these searches and make AI decision making more efficient. To take us through the different pruning techniques and their impact on multiplayer games, I would like to invite Anirudh to continue the presentation. Over to Anirudh.
Thank you, Sai Sri Pushpa. Greetings, everyone. I am Anirudh Kandwal, and now I'll discuss pruning techniques specifically applied to multiplayer game trees, known as max and trees. We will explore three main types of pruning: immediate, shallow, and deep pruning, and understand how they differ from traditional two-player alpha-beta pruning methods. First, let's clarify what exactly pruning is and why it's important. Pruning refers to techniques that aim to reduce the search space of a game tree by eliminating unnecessary branches. Game trees represent all possible moves and outcomes. Pruning significantly reduces the computational burden of searching this vast tree. By focusing on promising paths, pruning can improve performance and lead to faster decision making in complex games. These are three types of pruning: immediate pruning, shallow pruning, and deep pruning. First up is immediate pruning. Immediate pruning happens when a player instantly achieves their maximum possible score called max P at a given node. For example, in a three-player game, if two branches result in a score of 20, 10, 5, and 20, 12, 5, for the maximizing player, the first branch pruned since the second provides a better outcome. Similarly, if player 2 secures their top score by node B by choosing its first child and other nodes of B are irrelevant and prune immediately. Next is shallow pruning. Unlike immediate pruning, shallow pruning needs specific conditions, particularly a lower bound on each player's individual score and upper bound on total sum of scores called max sum. Here in this example, the node A and B demonstrates the shallow pruning, as node A's first value is greater than equal to 6 and node B can provide less than equal to 5. So we can prune this branch. The key lemma here it states that shallow pruning is only possible when max sum is strictly less than twice max P. Let's look at two examples, Hertz and surgeon major, to understand this better. In Hertz, there are 52 total points available, with each player able to get up to half of that amount, which is 26 points. Since max sum equals exactly twice max P, here shallow pruning is not possible. In surgeon measure, however, there are total 16 points available, equal to each player's maximum achievable scores. Here the inequality holds. So this game allows the shallow pruning. Next come deep pruning, which tries using bounds from ancestor nodes further up the tree rather than just immediate parents or siblings. Unfortunately, deep pruning usually doesn't work in multiplayer max and trees because deeper nodes can indirectly influence final outcomes significantly, even if they initially seem irrelevant. To visualize this idea clearly, imagine a player 1 has guaranteed minimum score at node A. Even if node D seems irrelevant initially due to earlier branch from ancestor like node A or B, it might actually affect players 3's decision making later down the line due to indirect dependencies between players' scores. Pruning strategy comparisons: two player versus multiplayer. In multiplayer games, alpha beta pruning is less effective due to complex player interactions. Alliances and indirect strategies make predicting more values harder, so shallow pruning is often more effective. Asymptotic results: best case is 1 plus square root of 4b minus 3 over 2, and the average case is b. B here represent brute force branching factor without pruning. An interesting strategy is reducing multiplayer games into a paranoid two-player scenario, where all opponents form a alliance against one player. This simplifies the game tree into a standard minimax structure, allowing effective use of alpha-beta pruning. However, this method assumes unrealistic cooperation among opponents, which can lead to suboptimal decisions in actual gameplay. Here you can see its asymptotic complexity, which is big of b ki power d cross n minus 1 over d. Here you can see the graph which shows the reduction to paranoid two player. Immediate to summarize today's discussion clearly, immediate pruning works similarly into both two player and multiplayer settings. Shallow pruning requires specific conditions relating individual lower bounds and total point limits. Deep pruning rarely applies effectively due to indirect influences among multiple players. Finally, reducing multiplayer problems into paranoid two-player games significantly boosts efficiency but may sacrifices realistic decision-making quality. Thank you very much for your attention. Next up is our friend Arpit Kumar with their presentation.
Thank you, Anirudh Kanwal. Hello, everyone. I am Arpit Kumar, and I will be discussing another very important pruning techniques for the multiplayer game tree, which is branch and bound. This algorithm is a powerful method for solving combinatorial optimization problems. It is a systematic explore the solution space by the branching, dividing problem into sub-problems and bounding, which helps eliminating invisible or sub-optimal solutions. The key objective of the branch bound is a clear find the optimal solution efficiently without resulting and exploiting search. Core component of the branch and bound. Branching split the original problem into a smaller sub-problems, bounding, estimating best or worst possible value for each sub-problems. This helps identify optimal branch. Pruning, cutting off sub-problems that can not lead to better solution than already found. This significantly reduces computational effort by the narrowing down of search space. Mm, the branch bound process. The overall process involves five clear steps. First, initialize, second branch, and third bound, and fourth branch. They repeat until iterative process you find the optimal solution. Advantage of the branch and bound. First is guarantee optimally. Uh, it always find the best solution, possible solution. Second, efficiency. Pruning significantly reduce unnecessary computation. Third is a versatility applicable across many combinatorial optimization problems like scheduling, routing, resource allocation, and more. Ch- challenges, limitations. Time complexity. In a worst case scenario, it may still explore an exponential number of the solutions. Second is memory intensive. Uh, storing multiple storing multiple sub problem can require consider memory resource. Third is quality of bound. Poorly estimate bound can lead to slower performance due to the fewer pruning optimization. Despite This limitation carefully implementation often imitation this issue effectively. Application area of a branch bound. A single agent branch bound, multi branch bound, traveling salesman problem, integer linear programming, job scheduling, knapsack problems. Optimization in branch bound, best first search, priority the most promised branches, cutting plans use inequality to refine bound and branch and cut, a hybrid approach combine branch and bound. Uh, yeah, this picture taken for multiplayer branch and bound. Here of at a road, two potential branch exist. Branch A value 790 for 7 plus 9 plus 0 equal to 16. Here is a hx equal to heuristic value, and makes some which is calculated by the all the possible outcome is 16 and makes pruning 16. At root node A, the value 790, heuristic S2 equal to less than 9 uh, kept initially but does not improve currently based. And branch B, heuristic H1 less than 5 pruned immediately as it's inferior to make sum equal to 6. Add branch D, split further sub branch C, here is C, which is H1 less than equal to 5 pruned due to insufficient potential. Other sub branches evaluate similarly, those not surprise maximum and prune immediately. Thank you. Pruning at set G, node with the x value value less than or equal to 5 are pruned because they cannot access the maximum known value equal to 6. Note that exceed and match the best known solution maximum sum equal to 6, they explore the further. The final outcome is the final tree retain only able branches that hold the potential to improve the solution, and the efficient pruning methods save computational effort by discarding less than promised branches. Thank you very much for your attention. Next up is our friends Ashish Kumar Gupta with their presentation.
Thank you, Arpit. Hello, everyone. My name is Ashish, and I will be discussing another very important pruning technique for multiplayer game tree, which is alpha beta branch and bond. This algorithm combines the technique of shallow pruning and branch and bond technique. Along with this, it also uses two heuristic bond. One is heuristic upper bound, which is maximum possible score for a player, and another one is heuristic lower bound, which is minimum guaranteed score for a player. Now let us look at the example to understand how this algorithm tightens the bond on player score and prunes more branches than shallow pruning. In this example, we have three-player max game tree. We have bound on the root of tree from its left branch. That is, player 1 is guaranteed to score at least 6, and hence player 2 and 3 can score at most max sum minus 6, that is 10 minus 6 equal to 4. Similarly, after searching the left child of node A, we get bound on max value of node A. We place an upper bound of 7 on player 1 score because player 2 is guaranteed at least 3 points, and 10 minus 3 is equal to 7. This value does not conflict with the partial max bound on the root, so we can't prune. We can have a bound from our heuristic, and if we combine this information, we can tighten our bond. We know from backup value that player 2 will get at least 3 points, and from heuristic that player 3 will get at least 2 points. So the real bond on player 1 score is max sum minus score of player 2 minus heuristic value of player 3, which is equal to 10 minus 3 minus 2 equal to 5. Now we can prune the right child of node A. It will be interesting to look at the actual algorithm. So this algorithm takes three arguments. First one is the pointer to the node structure. Second one is the player whose turn is, and the third one is bond for that player. So the first two lines here checks if the node is terminal. If the current node is terminal, then it will return the static value, that is the score value. Now the further two lines do the heuristic pruning, that is, it sees if the heuristic upper bound of previous player exceed the max sum minus bond, then it will prune that branch. Then it will recursively search the first child node to calculate the opponent's guaranteed point. It uses heuristic lower bound h low for all the player except the current and the previous player to tighten the bond. Here the pruning condition is if the current best score for the player exceed the bond minus heuristic, or if it matches the heuristic upper bound, it will prune that branch. Finally, we will update the best score. If the current node score is better than the best score, update the best score, and finally we will return the best score. Now let us look at the advantage of this algorithm. As we see that it prunes the branches by tightening the score of the player. So, so it in the best case it drastically shrink the search tree, especially in the perfect ordering and heuristic bond. It combines the strength of backed up score and heuristic bond. Next come the algorithm performance in actual scenario. This this table is the test result conducted on a game sergeant measure, and heuristic was number of tricks taken so far in the game. It searches 200 random trees to depth of 5 tricks. The number of nodes expanded by each algorithm varied widely. This algorithm reduces the node expansion by 18.7 factor with respect to shallow pruning. If you apply paranoid assumption, then the result gets further improved. We have now reached to the conclusion, and after discussion, we can say that ABB and B significantly reduces node expansion in max tree. However, it is not as efficient as two-player alpha-beta pruning. It is more likely to be working in the bridge game where we can search fully, but in multiplayer games like Sergeant Major and Hertz, it remains unsolved at this scale. So there is a need of further research in this field. More studies are required to find better pruning techniques for multiplayer game search. More search is needed to optimize search algorithm for practical use in the complex multiplayer setting. Domain-specific knowledge is needed to simplify the problem. Here are the references that we have used for our survey. And finally, thank you very much. And at the end, if you have any query regarding any of the pruning techniques discussed so far, you can contact via mail given here. Thank you.